Hi everybody, in this recording we will be going over section 3.6, a summary of curve sketching. So our main goal for this video is that you will be able to analyze and sketch the graph of a function. So in order to analyze the graph of a function, there are certain features or concepts that you need to recall from past sections. So your x-intercepts, or where the function crosses the x-axis, and that happens when y is equal to 0. Your y-intercepts, or where the function crosses the y-axis, and that happens when x is equal to 0. Symmetry, so this describes how a function mirrors itself across the x-axis, the y-axis, or the origin. The domain, so this is the set of all possible input values, usually your x values, for which the function is defined and will produce a real number. Your range is the complete set of all possible output values, so your y values, that result from plugging in the values from the domain. Continuity, vertical asymptotes, differentiability, relative extrema, concavity, points of inflection, horizontal asymptotes, and infinite limits at infinity. So these concepts are very useful in analyzing the graph of a function. So here are some guidelines for analyzing the graph of a function. Our first guideline states that we need to determine the domain and the range of the function. The second guideline states that we need to determine the intercepts, the asymptotes, and the symmetry of the graph. And then lastly, we need to locate the x values for which the derivative and the second derivative of f are either 0 or do not exist. Then we can use these results to determine the relative extrema and the points of inflection. So here we are given the rational function f of x is equal to x squared minus 1 divided by x squared minus 4, and we are told to analyze and sketch the graph of that function. So first we can use the original function to find certain features, such as our x-intercepts, y-intercepts, our vertical and horizontal asymptotes, and the domain and range. So our x-intercepts occur at y is equal to 0. So we will set our function equal to 0, and that happens at the points x is equal to -1 and x is equal to +1. So that's when our function crosses the x-axis. Now for our y-intercept, that happens when x is equal to 0, so we will evaluate f of 0. And that happens at the point 0, 1/4, so when y is equal to 1/4. Now for our vertical asymptotes, we set our denominator equal to 0, and in our denominator we have a difference of squares. So we have x squared minus 4. So we can factor that into x minus 2 times x plus 2 and see each of those equal to 0. So that means that our vertical asymptotes will happen at x is equal to -2 and x is equal to +2. Now for a horizontal asymptote, we have the same degree in both the numerator and the denominator. We have x squared in both the top and the bottom. So that means we will be dividing our leading coefficients. So we have a 1 in front of the x squared in the numerator and a 1 in front of the x squared in the denominator. So 1 divided by 1 will give us 1, and that's how we got the horizontal asymptote y is equal to 1. Now our domain is all real numbers except x is equal to +2 and -2, so our vertical asymptotes. And we can see because when we plug in +2 into our denominator, we get 2 squared minus 4, and we get 0. So division of 0, or dividing by 0, yields undefined. Now for our range, all real numbers except y is equal to 1 are horizontal asymptote. Now we can use our first derivative to find our intervals of increasing and decreasing, our critical number, and our relative maximum. So using the quotient rule, our first derivative, f prime of x, is equal to -6 divided by x squared minus 4 squared. So we can construct our test intervals and then choose test values between those intervals, and then determine if the sign of our derivative is positive or negative, and that'll tell us if our function is increasing or decreasing. So our intervals of increasing occur on the open intervals -∞ to -2 and -2 to 0. So that is where our first derivative is greater than 0. Our intervals of decreasing happen on the open intervals of 0 to 2 and 2 to infinity. So that is where our first derivative is less than 0. So our function is decreasing. Now our critical number happens at x is equal to 0 because our derivative changes sign. And lastly, we have a relative maximum at the point 0, 1/4. So our derivative changes sign from positive to negative. So now we can use the second derivative to find our intervals of concavity upward or downward and our points of inflection. So using the quotient rule, we get that our second derivative is equal to 18x squared plus 24 divided by x squared minus 4 squared. So the intervals of concavity upward occur from negative infinity to negative 2, and from 2 to positive infinity, because our second derivative is greater than 0. Now our intervals of concavity downward occur from negative 2 to 0, and from 0 to 2, because our second derivative is less than 0. Now we have no points of inflection because the second derivative does not change signs at any point. Now using all the information that we just collected, we can graph the function f of x, and here it is on the right hand side. Now here's a summary in a table form of the test that we just conducted for the first derivative and the second derivative, and how we can interpret those to describe the characteristics of the graph. Here's another example of sketching the graph of a rational function. So we have f of x is equal to 2x divided by the square root of x squared plus 5. Now using the function f of x, we can find the domain, the intercepts, and the horizontal asymptotes. So the domain will be all real numbers because the term underneath the radical, x squared plus 5, is always positive. Therefore, no real values can cause a negative square root or a zero denominator. So that means we will have no vertical asymptotes. Now the intercepts, the only intercept is the origin, the point 0, 0. And as for the horizontal asymptotes, we need to find the limit as x approaches positive and negative infinity of the function f of x. So in order to do so, we will divide each term by the highest degree of x. So you may think that the highest degree will be 2 because of the x squared, but because of the radical, once we take the square root of x squared, that gives us an exponent of 1. So that means that the degree in both the numerator and the denominator is equal. So we will divide each term by x. So for this problem, you will divide the denominator by x, but in the form of the square root of x squared. So once we do that, we're left with this expression, and we will be evaluating the limit as x approaches positive infinity and negative infinity of 2 divided by the square root of 1 plus 5 divided by x squared. Now, once again, using theorem 3.10, this term will go to 0, and we're left with 2 divided by the square root of 1. Since we're taking the square root, we are left with 2 divided by plus or minus 1. So that gives us 2 different horizontal asymptotes at y is equal to positive 2 and at y is equal to negative 2. Now we can use our first derivative to find the critical numbers, the intervals of increasing or decreasing, and our relative extrema. So f prime of x is equal to 10 divided by x squared plus 5 raised to the power of 3 over 2. We will get no critical numbers because if we set our first derivative equal to 0, we were dividing a constant 10 by x squared plus 5 in the denominator. So we will never get a 0 or undefined. Now for our intervals of increasing, because both the numerator, 10, and the denominator, x squared plus 5, are strictly positive, then f prime of x is positive everywhere on the interval. So it is always greater than 0. As a result, we will get no intervals of decreasing because f prime of x is never negative. Now for our relative extrema, we will have none because the derivative never changes sign. Next, we can use our second derivative, which is equal to negative 30x divided by x squared plus 5 raised to the power of 5 over 2 to find any points of inflection. So by setting our second derivative equal to 0, we will obtain that x is equal to 0 as a possible point of inflection. So now we can construct test intervals to see where our function is concave upward or concave downward. So for the first test interval, we are testing from negative infinity to 0. So when we evaluate a negative value of x, the second derivative is greater than 0. So that means that our function is concave upward on the open interval from negative infinity to 0. Now for the interval from 0 to positive infinity, when you evaluate a positive value of x, the second derivative is less than 0. So that means that our function is concave downward on the open interval 0 to positive infinity. So the concavity changed from upward to downward. So that means that x is equal to 0, the origin, is a point of inflection. Now here's a summary of the information that we just collected. So we have our 2 test intervals from negative infinity to 0 and from 0 to positive infinity, and we had our point of inflection at x is equal to 0. So at f of 0, we get 0. At f prime of 0, we have 2 divided by the square root of 5. On the interval negative infinity to 0, f prime of x is positive. And on the interval 0 to infinity, f prime of x is also positive. Now, the second derivative, evaluated at the point 0 is also equal to 0. And we get that on the interval negative infinity to 0, it is positive. But on the interval from 0 to positive infinity, the second derivative is negative. So that means on the first test interval, our function was increasing in concave upward because it was positive for both the first and second derivative. But on the second test interval, it was increasing because our first derivative was positive, but concave downward because our second derivative was negative. So that means that x is equal to 0, once again, is a point of inflection. Now, here we have the graph of our function using all the information that we just collected. Here's another example, but this time we're provided a trigonometric function. So we have f of x is equal to cosine of x divided by 1 minus sine of x. So because the function will repeat itself in intervals of length 2 pi, or it has a period of 2 pi, you can restrict the analysis of the graph to any interval of length 2 pi. So for convenience, we choose the open interval, negative 3 pi divided by 2 to pi over 2. So first we use the original function, f of x, to find our x-intercepts, y-intercepts, vertical asymptotes, and symmetry. So our x-intercepts happen when y is equal to 0, and we get that that occurs when x is equal to negative pi over 2. Our y-intercepts occur when x is equal to 0, so we plug in 0 for f of x, and we get the origin, 0, 0. Now for vertical asymptotes, we let 1 minus sine of x equal to 0, our denominator, and we obtain that x is equal to negative 3 pi over 2, and that x is equal to pi over 2. Now for symmetry, we will evaluate f of negative x. And we will obtain that f of negative x is equal to negative cosine of x divided by 1 plus sine of x. So once we simplify, we will get that f of negative x is equal to negative f of x. So that means that f of x is an odd function whose graph is symmetric about the origin. So next we can use our first derivative, 1 divided by 1 minus sine of x, to find our critical numbers, our intervals of increasing, and our relative extrema. So we will have no critical numbers because the numerator is a constant, 1, and the denominator exists in the period. Now for our intervals of increasing, by evaluating a value of x in the interval, you can see that f prime of x is always going to be greater than 0 or positive for the values of x in the interval. So that means that our first derivative increases in the interval negative 3 pi over 2 to pi over 2. For our relative extrema, we will have none because f prime of x does not change sign in the interval. It is always positive. So now we can use our second derivative, f double prime of x is equal to cosine of x divided by 1 minus sine of x raised to the power of 2 to find any possible points of inflection. So setting our second derivative equal to 0, we see that that happens when x is equal to negative pi over 2. So that means we can cut our interval from negative 3 pi over 2 to pi over 2 into two intervals. The first one being from negative 3 pi over 2 to negative pi over 2. And we will test the second derivative by choosing a test value. So we get that the second derivative is less than 0. So that means that the function is concave downward on the interval negative 3 pi over 2 to negative pi over 2. Now for the second interval, from negative pi over 2 to positive pi over 2, choosing a test value, we get that the second derivative is greater than 0. So this means that f of x is concave upward. So that means we have a point of inflection because our second derivative changes from negative to positive at x is equal to negative pi over 2. So our point of inflection is that x is equal to negative pi over 2, and we have our corresponding graph of f of x to the right. Now here's a summary of all the information we just collected. We have our test interval from negative 3 pi over 2 to negative pi over 2, our point of inflection, x is equal to negative pi over 2, and our other test interval, negative pi over 2 to positive pi over 2. So the first derivative on this interval is positive, so that means that the function is increasing. The first derivative on the interval negative pi over 2 to pi over 2 is also positive, so that means that the function is increasing on that interval. The second derivative on the interval negative 3 pi over 2 to negative pi over 2 is negative, so that means that the function is concave downward on that interval. And now for the other interval, negative pi over 2 to pi over 2, the second derivative is positive, so that means that the function is concave upward, thus confirming our point of inflection, because it changed from concave downward to concave upward. Now, since we have a vertical asymptote at negative 3 pi over 2 and at pi over 2, the functions do not exist once we evaluate at x is equal to negative 3 pi over 2 and at x is equal to pi over 2.